Hello, everyone. My name is Bhaskaram, and this is going to be a quick video about a couple of diverse topics. So we're going to very quickly look at the S-plane and gain phase margin, gain margin and phase margin. Then we're going to look at the relationship between gain bandwidth product and unity gain bandwidth. We're also going to talk about the relationship between 3 dB bandwidth and the time constant, and similarly for pole location and transient response. And then we're going to look at the damping factor and natural frequency in a second order system. And then we're going to look at poles and zeros in the right-hand plane. So usually we have poles and zeros in the left-hand plane, but we're going to look at the phase and gain of poles and zeros that exist in the right-hand plane. Okay, so let's get started. S-plane, so S is sigma plus j omega. So here's the real part, and j omega is the imaginary part, and sigma is, we have the real axis over here and the imaginary axis over here, all right? And then whenever we have a transfer function, we usually try to simplify it to something of this form, where we have a DC gain as a sort of like a quote unquote prefix of the equation. And then any terms that are at the top, any S terms that are at the top, those will be the zeros. And any terms at the bottom, any S terms at the bottom would be the poles. Okay, so, and let's look at the, I've drawn a hypothetical, basically, magnitude plot over here. So we can quickly take a look at some of the things that are important. First is a DC gain. And then in this example, we have a zero first, where we start rising 20 dB per decade. And then we hit a pole here, at which point the magnitude flattens out. And then we hit a second pole where now we start to fall 20 dB per decade. And somewhere along the lines, we would also have the 3 dB frequency. And then at one point, we will have the unity gain bandwidth, which is the bandwidth or the frequency at which the gain is 0 dB. And then we could also have poles after the unity gain bandwidth, for example, here. And then the point is that when you accumulate more poles, then you would add 20 dB per decade rate. So for example, here we have 2 poles, so we're dropping by 40 dB per decade at this point. Again, and you can look at the 3 dB frequency and similarly unity gain bandwidth. 3 dB bandwidth and unity gain bandwidth. All right, so let's look at the gain margin and the phase margin. So phase margin is basically whenever the gain is 0, you look at the phase and see how far away you are from a point where in the loop you would have 360 degrees of phase shift. And depending on the number of degrees that you're far away, that's your phase margin. In this case over here, and then similar idea for gain margin. If the phase in this example when the phase is 180 degrees, you look at the gain and you look at how much your gain and how much below is it from the 0 dB point. So that's the gain margin. So the further below you are, below 0 dB of gain, the more margin you have, the more gain margin you have, to be specific. Okay, so let's quickly look at the relationship between 3 dB bandwidth and tau, which is the time constant. So I've seen this usually where somebody asks you what's the 3 dB bandwidth or the 3 dB frequency, and if you can see the time constant of the circuit, and you can find out the tau, then you can use this equation to find out the 3 dB frequency. Or conversely, if you know, if you know the 3 dB frequency, then you can find out the time constant of the circuit, and you can make calculations about how your rise time and fall time would look like, or how the response would settle, because you know the time constant tau. So that's the relationship between 3 dB frequency and tau. And then we have the relationship between the unity gain bandwidth and the gain bandwidth product. So in a single pole system, we would have the unity gain bandwidth would be equal to the product of 3 dB frequency and the DC gain. In this case, it's A. So that's the unity gain. And that will be equal to f0, which is the unity gain. So this point will be f0 is equals to f minus 3 dB multiplied by the DC gain A. Now, in a single pole system, this would also be equal to the gain bandwidth product. Gain bandwidth product. So that's a relationship between gain bandwidth product and unity gain bandwidth. Basically, they're equal in a single pole system, and they can be found out by multiplying the 3B frequency multiplied by the DC gain. Okay, moving on. Let's look at the relationship between pole locations and the transient response. So here I have 5 cases. That doesn't mean that these are the only possible cases. There's other cases as well, but I've mentioned 5 cases over here. So let's look at case number 1, where we have both poles in the left-hand plane. But this would be the low frequency. Sorry, this would be the low frequency pole, and also sometimes called the dominant pole. And this would be the non-dominant pole or the fast pole. The idea is that this dominant pole is basically low frequency, so it's I guess dominating your system. It's dominating your response, or it's affecting how fast or how slow rather your response settles. So that's where the dominant part comes from. So that's the pole that matters, or that's the pole that's limiting your bandwidth, right? So yeah, that's the dominant pole. And then in the the time domain, by the way, I have voltage over here as the y-axis, but it could be any quantity. It could be current, it could be phase, it could be whatever, right? I've just written voltage as an example, but essentially you would get a response something like this, where it's for a step input, by the way. So all of these responses are for step inputs, okay? And yeah, you would get a response like this. And then case number 2. So by the way, the thing to notice here is that in case number 1, the poles are on the real axis or the sigma axis. In case number 2, the poles are have some real component, and they have some j omega component or some imaginary component as well. So these are complex poles, and and when you have that, then you have some ringing, and the idea is that the more j omega component that the poles have, the more ringing you're going to see. And so as an example, over here, let's say the poles are on the j omega axis, and so you're going to see pretty much ringing all the way. In fact, in this case, it's not even ringing, it's just a sine wave, and this system would be unstable, right? And in case number 3, you don't have any real component in the poles. All of the component of the poles is just imaginary, so which is why the poles are just on the j omega axis. Okay, case number 4. Now the poles are in the right-hand plane. So here you would have exponential kind of response. And if you have, in case number 5, if you have an imaginary component, again, the j omega component, then you're going to see some sort of an oscillatory response. And so you would have, an exponential, but some ringing or some oscillations as well, which are sort of blowing out. And so case number 4 and 5, and even 3 is something that we don't want to see usually in our circuits. Case number 2 is something that we deal with and we try to limit the ringing. Case number 1 is, I guess, I wouldn't say ideal, but usually much better than case number 2. Anyway, by the way, I guess I shouldn't say that we totally do not want case number 3, 4, and 5. As an example, let's say you're designing an oscillator. So you want your output to oscillate, right? So do you think like there's value in intentionally placing your poles somewhere in the right-hand plane and making sure that they have some sort of imaginary component, so that you get a sine wave, and you get a sine wave that doesn't die out. In fact, it blows up, and it keeps happening until infinity time. So do you see how we can use the concept of instability to build oscillators, right? So all of these statements about like stable and unstable, you can't really say like we never want unstable, because there's circuits where we actually value and we're intentionally trying to build unstable circuits because we want them to oscillate, right? Okay, so as on the S-plane, usually the trends are that if you move towards the left, the time domain response will settle faster. When you move up, the frequency of the ringing will increase, so the oscillations will be faster. Okay, and this is the good zone where you don't see any oscillations, or should I say the quote unquote good zone, again depending on the circuit that you're trying to design, but usually this is desirable in most cases. So you get left hand poles that are totally real. That's going to give you a good time domain response for a step input. And then anything on the right hand plane, so any poles over here, you would get an unstable response or something that blows up, and usually that's undesirable. So yeah, that's how you can view the poles in the S-plane. All right, let's look at some of the things with a system that has one integrator in the loop and two integrators. So let's imagine we have one integrator over here, which is 1 over S. And if you have a step response, then at the input, then a system like that, if you have one integrator in the loop, then the system would be able to track the step, right? So that's okay. But what if you give a ramp to a system like this with just one integrator? So then this system would not be able to like completely or properly track this ramp. In fact, there would be some sort of static phase error that happens. So how do you deal with that? Well, if you have two integrators in the loop, then it can track a ramp input, and it would be able to basically give you an output that tracks the input, the ramp input, with very little static phase error. So that sort of looks a bit random in this video, but essentially this may or may not be, this may be something that you see when you're looking at the theory of any analog circuit. For example, one place where I saw it is when I was studying CDRs. So if you have a CDR with one integrator, and here in the y-axis you have phase, because CDRs are trying to look for or trying to deal with like phase and frequency as inputs, right? So if you have a phase step, then a CDR with one integrator is able to track it, but CDR with one input is not able to track if the phase is if it's a ramp input for a phase, and you get a static phase offset. So then you can have an integrator with two. You can have a CDR with two integrators, and then it would be able to track a phase ramp at the input. Yeah. So again, this is not to say that this is just relevant for CDRs. You might see this for other analog circuits as well, but I just wanted to make a quick note of it in this video. Okay, so let's look at a damping factor and natural frequency of a second order system. So second order system, because S has a power of 2, and this system would have 2 poles as seen in this transfer function. Now these poles might be real or complex, but the idea is that you can write this transfer function as something of this form, something in the form of omega n, which is the natural frequency, which we call the natural frequency or frequency of oscillation, and zeta, which is the damping factor. So the reason we are trying to sort of write our transfer function in this form is because we want to see, imagine if I wanted to, if I wanted you to calculate, where you are in terms of damping. So let's say you have a second order system that rings, and I'm trying to ask you, what will be the frequency of the ringing? what will be the damping? If you want to reduce the damping, what should you do? How do you vary the frequency of the ringing? So all that sort of system that could so all that sort of all those sort of I guess questions you could answer if you sort of arrange your transfer function in this form, and then you can find out the omega n, which is the natural frequency of the ringing, and then zeta as well, which is the damping factor of the ringing. And so the idea is that for a zeta of 0, it's an undamped system. So you would get, let's say, a sine wave that doesn't die out. For an underdamped system, you would get a sine wave, let's say, that eventually dies out. It's not properly damped, but it's underdamped. But it will eventually die out, the ringing. Critically damped is like you get, let's say you have a step input and you get an output that basically, as quickly as possible, it will basically track the step input. And overdamping is, again, if you have a step input, your output tracks the input, the step input, but it takes more time than, I guess, necessary to track the input. So that's overdamping, because you can have less damping and you can track you can settle your output can settle faster without introducing ringing, I guess. So critical damped is usually the nice case where you're not wasting any time and your output is settling to the input and you're not getting any ringing. So let's look at it in terms of S-plane and time domain, right? So undamped case, again, like I said, it could look something like this, where you have a sine wave, and this would be omega n, the frequency of oscillation, and this would be a case like this, where your basically the imaginary component is all that exists for the poles, and so you're gonna get an oscillation that propagates till infinity. And then there's the underdamped case, where the poles still have an imaginary component, but they also have a real component. And your zeta would be somewhere between 0 and 1 in this case. And you would get some ringing, but it will eventually die out. So that's underdamped. Critically damped is when the poles are overlapping on top of each other. And so there's no, like, in a way, both poles are equally dominant. And so both poles are real and they're equal. And this is a zeta of 1. And again, your output tracks the input without wasting any time. Overdamped is when you have one pole which is fast, but then there's another pole which is slow, or in other words, a dominant pole which is limiting your response and your settling time. And this is a zeta of greater than 1, and the response could look like this. In comparison to, for example, let's say here, sorry, in comparison to, let's say, of this graph, this one, the one that's below, is taking more time to settle to the input. Okay. So yeah, that's the sense of like omega n and damping factor for a second order system. And so I guess from this graph, you can also see that, you can increase the damping factor and that would reduce the ringing. Yeah, and then omega n tells you the natural frequency or the frequency of oscillation, if you need to look at that or calculate that. All right, so let's look at poles and zeros in the right-hand plane. So, okay, let's first look at the left-hand pole. We have a transfer function, we have the S-plane, we have a gain plot, and then we have a phase plot. So the transfer function is 1 over s plus 1. This is just an example. You can take whatever expression that gives you a pole anywhere in the left-hand plane. But I've chosen like 1 over s plus 1. So that gives us a pole at sigma of -1. And yeah, again, like you would get a 20 dB drop and the phase will drop by 90 degrees. So that's pretty normal. We see that every day, right? But let's look at the right-hand pole. So that would be, for example, 1 over s minus 1. So here you get a pole in the right hand, and your gain still drops by 20 dB per decade, but now the phase sort of, increases, kind of like a zero, and again, let's look at the left-hand zero, which is a normal thing that we see. It's, your gain would increase by 20 dB per decade, and your phase increases by 90 degrees. So great stuff. But then let's look at the right-hand zero, where the gain increases by 20 dB per decade. However, your phase falls by 90 degrees. So kind of like a pole, because the phase drops when you have a left-hand pole, right? So this could be relevant in like different designs. I guess one of the places, for example, would be a two-stage OTA. So let me quickly draw a two-stage OTA. And this would this is sort of something that you might see when you're reading about compensation, the Miller compensation for a two-stage OTA. So two transistors in a diff pair, and then some sort of current. I'm just drawing like a very rough and a very quick diagram, right? And then here you have the output from the first stage, and then it goes to the input of the second stage. Say a PMOS here, and then an NMOS over here. So that's the lower NMOS is just bias voltage, right? Okay, so then Miller compensation is something like this, right? You add a capacitor over here, and this is the output. So then this capacitor, if you look at the S-plane, it would, if this is the J omega, and this is sigma, then adding this capacitor would add a zero over here, which is exactly like the right-hand zero that we were talking about. And so the problem is that this kind of zero acts like a pole, and it would start dropping your phase mark, because the phase drops when you have a right-hand zero. Then you would have a lower phase margin if you have this right-hand zero. And so the idea is that somehow we have to turn this right-hand zero into a left-hand zero. And one way we can do that is by adding a resistor in series. So you can like derive the transfer function of this, but essentially, depending on the value of this resistor, this zero would basically come over here. So it would be a zero in the left-hand plane now, which is a good zero. It's increasing our phase, right? So yeah, that's basically the idea of like, sometimes you might read something in which might say, right, we got a right-hand zero that's acting like a pole. So that's what they mean. Basically, it's reducing your phase, which is bad, and you don't want to do that. And so yeah, that is pretty much it for this video. Let's look at the contents. Yeah, we discussed the S-plane, gain margin, phase margin, relationship between gain bandwidth product and the unity gain bandwidth. Both of them were equal for a single pole system. We discussed a quick relationship between the 3 dB frequency and the time response. Sorry, and and the tau. And then relationship between pole location and transient responses. We looked at, where different poles land on the real axis or imaginary axis, and how we get, a good response, a good step input response, and then, a response with bringing in stuff. And then we looked at the damping factor and natural frequency for a second order system. Again, the damping factor would tell us like how good of a job are we doing in terms of damping out any ringing, and omega n is the natural frequency of that ringing. And then we looked at the poles and zeros in the right-hand plane, and how, for example, a right-hand zero can reduce our phase, and so acting like a pole, and it acts like a pole that's in the left-hand plane. And then we also looked at the pole in the right-hand plane, which actually acts like a zero in a left-hand plane. All right, so that is pretty much it for this video, and I'll see you in the next one. Cheers.